Great. So what we saw was, make sure it's showing, oh no, make it big. So what we saw was previously we ended with this, reordering it to this form, and now I can say let's go back to our strong form and rewrite our strong form by using the information that we've derived in this weak form. So essentially I'm pulling in my equilibrium equation plus my tractions. So this is why you won't see the tractions featuring here. So this is now a combination of the equilibrium plus the tractions in one form. This is a scalar equation, but if I were to take derivatives with respect to W, I would end up with a system of equations for which I can solve sort of these parameters that control what's going on in this sigma. Remember this C parameter that we spoke about. We have the constitutive equations. So this relates strain to stress. Displacements get related to strain. Prescribed displacements where we have prescribed displacements. Additional thing that wasn't there before that is important is wherever we have a prescribed displacement, we have to make sure we enforce that the weighting function is 0 there. So this is all that this does essentially. So saying this is additional condition that comes in this weak form. It's just the weighting function needs to be 0 where we have prescribed displacements. What this means is, what this implies is that whenever we have prescribed displacements in this problem, and because this weighting function will be 0 there, we will just recover exactly the displacement. So this displacement is not going to be approximated. So what I just want you to take note here is this U and this U bar. When I have a prescribed displacement of 1 millimeter in frame, I recover that 1 millimeter exactly. If I have a prescribed displacement of 20 millimeters, I recover that displacement of 20 millimeters exactly. So this ensures that I have an exact representation of the prescribed displacements where I apply them. This is important to understand. Okay, so this combination here. You know, I look at the tractions. The tractions, there's a chance that this might only be approximated because I'm sort of satisfying it in an integral fashion. So there's a good chance that this will be like the same way we did with the function with the residual. When we tried to satisfy the residual, we didn't satisfy it exactly, but we find the minimum error one. The tractions will be found in such a way that it will minimize the error as well. Okay, but remember that the union of where we apply tractions, so this is the area integral of tractions, and the places where we apply displacements, prescribed, makes up the whole body. There's nothing left out here. Okay, and where we have prescribed displacements, we have free action tractions. Where we have prescribed tractions, we will solve for displacements, and everywhere else we also solve for displacements. Okay, so let's look at what is going on now in this problem. What are the fields and what are the unknowns? So now we have essentially 3 fields for W. W for the X displacement, Y displacement, Z displacement with a big W. We essentially have a displacement field that's dictated by C, but there's 3 of them. That's a displacement X, Y, and Z direction. Yeah. So this is a vector of displacement fields, but this is controlled by C. I can relate this U to epsilon using these partial derivatives. Yeah. Then I sit with the strain. This is 6 strain fields with unknown C's, but these C's are related by this C's that I've chosen from this W. They get pulled through. The strain, I can just with algebra multiply with the matrix of the material, boom, and recover my 6 stress fields, which is also created by the C. This is the stuff that I need to try and do now. So what we see here is, this is now, we've taken the strong form, which was only 15 fields of unknowns, yeah, before. We actually now have 18 fields of unknowns. There's 3 here, 6 here, 6 here is 15, plus another 3 is 18. But when I take the partial derivatives of this W with respect to these big W's, I will recover essentially additional unknowns, of the additional equations, yeah, that will allow me to solve for the algebraic system of equations for the C's. This is important. So here I sit essentially now with 18 equations, 18 fields. Apologies, let me just quickly cough. Sorry. Sit here with 18 fields, but we're still going to be doing something later on where we essentially going to be taking derivatives with respect to these unknown variables W that allow us to get sort of a system of algebraic equations from which we can solve the C's. Okay, so this is just to make sure that we understand what has changed. The tractions are pulled into the equilibrium equation, and that's giving us this scalar equation here at the top. Then there's all this other stuff that we've had before, plus there's this W that's new, making sure that when we have prescribed displacement, they are exactly satisfied, they're not approximated. And then our problem now essentially has 18 fields that we need to solve for. There are these C variables plus these W variables. So the number of unknowns are C plus W. That's really what we have. But we will take derivatives with respect to all of these W's, and that will give us the same number of equations than the unknown C's. Because the C's and the W's are sort of coefficients of the same form of equations. Remember, the W and the U's will have the same form. It's just we will call these coefficients maybe A, B, and C, and these ones we call D, E, and F. Okay, so hopefully this is making sense to you, that this is the problem that we're going to be approximating using finite element method. And this is now derived using the weighted residual method. Okay, there's one thing that I need to talk about before we continue, before I end this video, and this is this double contraction. This double contraction, what is that? Because remember, this follows from the fact that we took, I just want to remind you again where it came from. This follows from this identity where we had the divergence of the matrix vector product is equal to the divergence of the matrix multiplied by, dotted with the vector, plus then the matrix multiplied by the divergence of this vector. Matrix multiplied by the divergence of this vector. This is where this double contraction, because this is essentially just the gradient of G with respect to X. This is a matrix, and now this double contraction is the double contraction between two matrices. Okay, to get a scalar out. Let's check. So this double contraction operator is just as follows. Essentially, I have I'm just defining a W field, again, making sure it's understandable. There's the W related to the U displacement, V displacement, and W displacement. This is now with a transpose. It typically would be a column vector. The transpose allows me to write it as a row vector. And now I can say, this double contraction operator, what does it do? Okay, so first off, let's just look at what is this, the partial derivative of V with respect to the partial derivative with respect to X. There's a partial here missing. Apologies for that. It should look like this. Okay, there's a partial missing there. So essentially what we see is I take the W field and I take the derivative with respect to X, Y, and Z, the partials with respect to X, Y, and Z. That's the first column. Then I take the V, so this is what this looks like. This partial of a vector with another vector will give us a matrix. First entry, partial derivative with respect to all the variables of X. Second entry, which is WV, partial derivative with respect to X, Y, and Z. WW, partial derivative with respect to X, Y, and Z. That's it. Okay, so this is the one matrix that we have from the stress side. This is now this matrix we get from this gradient of the W with respect to X. Okay. Now what I do is I do this double contraction, and the double contraction is simply the following. Simply the following. It's a scalar quantity that pops out here. So it's not just a single dot product, it's a double dot product. All I'm saying is take this, multiplied with this, this dotted with this. So this multiplied with this, plus this multiplied with this, plus this multiplied with this. This is what I see here. Plus this multiplied with this, plus this multiplied with this, plus this multiplied with this. That's what I see here. And then plus this multiplied with this multiplied with this, and this multiplied with this. That's what I see there. And all of them sum together, that's what the double contraction means. Simple as that. So this is just to make sure that you can now follow and understand what we are doing here. Again, this double contraction, that's my scalar here. T dot with a W is another scalar. W dot with the F is another scalar, because these are just all vector fields. Okay, vectors. So vectors, although they contain fields and functions inside, they are still just vectors. Okay, spatial vectors of X, Y, and Z. I hope this gave you a good overview of where we are now. So now we're essentially ready to start doing the finite element method for the first time. But please bear in mind, we're not going to solve the strong form as we've done before and check for equilibrium on the strong form when we do finite elements. I still want you to be able to do that when I give you a solution. But with the finite element method, we have now recasted that strong form into what's called a weak form, where we can now work with approximations. We can now have approximations for U, approximations for epsilon, and approximations for sigma. Now we are ready to do FEM.